Okay, good morning, everybody, to the second day. So Professor Alessandro Ghigi will speak about differential geometry of the Torelli map.
The plan of what I'm going to say is the following. First, I will remind you something about the second fundamental form in Riemannian geometry. And the rest of the talk will be about the computation of the second fundamental form of the Torelli map, the Torelli embedding, so outside the hyperelliptic locus. And we will start by some constructions which are called Hodge-Gaussian maps. I will define these and I will show that they are well defined. Next, there is a step which I will jump over, and I will just state that the second fundamental form is a Hodge-Gaussian map. And finally, I will get a first formula for the second fundamental form, from which it will be clear that that the second fundamental form is an object of Hodge theory. Although quite complicated. And probably tomorrow I will get let's say apparently better formula, which means that the formula looks nicer, but in the end it is not much more clear how to compute it. So let's start with the first point, and let's go back to the setting of a Riemannian manifold. So G is a Riemannian metric, and assume that we also have a submanifold. And what is the second fundamental form? The second fundamental form, which I abbreviate this way, of X in Y is obtained as follows. We start from the sequence of vector bundles, of tangent bundles on X. Here N is, in principle, could be the, in this setting is just the orthogonal of the tangent to X, but of course it is isomorphic to the quotient of the first two, and this is this point of view is better in the complex case. So I will usually think of it as a quotient, and I will denote this map by pi, although in the original, in this original sense, pi of a vector is its perpendicular component. Okay, so next, since this is a Riemannian manifold, it has a Levi-Civita connection. And if we have two vectors, so first of all, the second fundamental form turns out to be a map like this. So you want an element, a section of this bundle. And it is defined in this way. If U and V are two tangent vectors to the submanifold, first of all, we extend V to a vector field, local vector field on X, and then we set, then we can compute this derivative, because if this is X inside the Y, let's say that Y is simply R3 for the picture. Then here we have the two tangent vectors. And I have extended V to a vector field in a neighborhood of the point. Then if I want to compute this derivative, I just need to choose a curve here that is tangent to U. So if gamma t is tangent to U, which means this, then I can compute this derivative right here as a covariant derivative along gamma. This is okay. This in general, this thing in general will be a vector in the whole manifold. So this is computed in X. This will be a vector here. And then we project to the normal component. And this is exactly the definition of the second fundamental form. And the point is that, first of all, it does not depend on the chosen extension. So it is well defined. Next, it is bilinear. It is also symmetric. So here we could put, instead of just this, the symmetric part. And that's it, basically. So maybe before going further, it is better to recall something. So for example, an important concept related to second fundamental form is when it vanishes completely. So if Z is a submanifold of Y, we say that is totally geodesic. If the following holds, if for any point here and for any vector tangent to the submanifold Z, the unique geodesic of Y, let's call it gamma, the unique geodesic with these initial data, so the unique gamma such that gamma 0 is X and gamma dot is U. So the condition that I have to put on this geodesic is that it stays inside Z for, let's say, for small times. So for t less than some epsilon. Okay. If we think of the most familiar case, it is when we have a surface inside 3 space. Geodesics are just lines, so we are asking that the line tangent to our surface stays within the surface at least for a small time. And so totally geodesic submanifold are generalization of exactly like lines and planes in R3 or affine subspaces in Rn. And okay, so it's quite easy to check this fact that Z is totally geodesic. If and only if the second fundamental form of Z inside Y vanishes identically. So this is the case where the second fundamental form is trivial. And actually, we might also here remark that usually a general Riemannian manifold has absolutely has very few totally geodesic submanifolds. So if you take the sphere and you deform the metric in some way, there are no totally geodesic submanifolds anymore. But if the ambient is a symmetric space, in particular, if the ambient is the Siegel space, then there are a lot of totally geodesic submanifolds. And the final point, another thing that is very similar to this and it is quite easy to prove, if we have this situation, so Y is our ambient manifold, X is a submanifold, and Z is totally geodesic. Then the second fundamental form of the submanifold in the middle, let's denote like this. This here vanishes identically on the subspace given by the tangent to Z. So the second fundamental form of X is defined like, okay, I'm traveling too much. The second fundamental form of X is like this. Inside here we have the tangent to Z. Of course, this works if I choose Z inside here. And then the second fundamental form vanishes identically if the two vectors belong to this subspace. So this can be used to check this can be used, let's right here. Second fundamental form is useful to check if some submanifold contains totally geodesic submanifolds. And if we go back again to the familiar picture of surfaces in R3, this says that we can use the second fundamental form to check if a surface contains a line, for example, or if we go in higher dimension, if we have a submanifold of Rn, if it contains a plane, let's say, then the second fundamental form of the submanifold should vanish along the directions of this plane. Yeah, sorry. Sorry. No, because I mean no, this is not the case. No, because you can take if you take this R3, this plane, and this any curve, any plane curve. You have a plane, have a curve on it. Then the second fundamental form of the plane vanishes, but Z is not totally geodesic, so it's only one way. Yes. Yes. For example, if you take the round sphere, this is a symmetric space, and if you take these ones, these are the equators. These are totally geodesic submanifolds. In fact, they are actually closed geodesics. But if you work in Sn, and you take any Sk, in between you get, so, and this in fact is an example of a symmetric subspace, sorry, of a symmetric space, and these ones are the kind of, so for example, in symmetric space, everything boils down to Lie algebras, and one can check with Lie algebras that there can be a lot of totally geodesic submanifolds. Although it is not at all easy to compute all of them. So it's definitely explicit, but it's not trivial. Yes, exactly. Exactly. That is an if and only if. So it's totally geodesic if and only if it is a symmetric subspace. Exactly. So it is something that one can check with the Lie algebra. Okay, so this is the second fundamental form, and now let's go to Hodge-Gaussian maps. So here we start a little bit more general. So let C be a curve, a smooth, complete curve over C, and fix a line bundle. And we assume that it has some sections, otherwise it's trivial. And denote by M the multiplication map of sections. So we have if we take a simple decomposable tensor, we send it to this section. And this is symmetric, so we can look at it as a map from S2 to H0 of L2. And I'm pretty sure I will use both notations for line bundles. So sometimes I will use additive notation and sometimes multiplicative notation. I know that it is wrong, but I will probably make this mistake. And by this, of course, I mean tensor product. Okay, and so the kernel of M is denoted in this way. The 2 means that we can also consider product of P sections, and then we will have an IP, but we only need I2. Okay, now the Hodge-Gaussian map will be a map like this. Can you see there? I2 is the kernel of M. So is the set of tensors here that when multiplied go to 0. So this is the definition of the symbol. So the Hodge-Gaussian map will be a map like this. Here, L-1 is simply the dual line bundle. And okay, so let's go to the definition. So we take an element here. This will be something, will be an element of this tensor product, symmetric tensor product. So this means that SI are sections, and actually we can assume that this is a basis of H naught. The AI are numbers, and since this is symmetric, they are symmetric. And okay, next, take an element here. And we will use Dolbeault theorem constantly. So this E will be the class of some 0-1 form with values in L-1. Okay, now we use this phi and this basis and consider these products. Now, this is a 0-1 form with values in L-1, while this is a section of L. So this product means that we contract L and L-1, and what we get is a 1-0 form on the curve. And now we use the Hodge theory. So this 1-0 form, sorry, 0-1 form is of course closed. And so it will be, so it will define a cohomology class. This cohomology class will have a harmonic representative. So this is the harmonic projection of this form, which is closed. And the difference will be the bar of something. And now the definition is the following one. Here I'm always summing over all indices, so I get all the okay, so yeah. So let's see at least that makes sense. So this is what? This is a 1-0 form. And this is something that lies, is a section, sorry, this is not Y, is S. This is what? This is a number, this is a section of L, so this part here is a section of L. So at least it is likely that we end here. Now we have to check this. So we have to show that this is well defined. And this is due to Colombo, Pirola, and Tortora, who in fact they defined these maps. They defined in a much more general setting, but let's stick to this case. So this is well defined, which means it is holomorphic. So it is a holomorphic section of this bundle. And two, it is independent of the chosen representative, phi. And maybe it is better to stress that so usually when one has something on E, so it does not depend on phi. Thank you. So usually when one has this, one completely forgets about this part, and is, most of the time is not used. While here, in fact, it is used and it is crucial to get something. Okay, so let's see at least one of the two verifications. Maybe since I'm already late, let's only see two. Proof of two. And okay, so we have two representative. Yeah, sorry, this is a Q. Q of E, thank you. Sure, yes. Okay, so we have two representative, and this means what? We want to check that the two definitions agree. And since they represent the same Dolbeault homology class, we will have something like this, where lambda will be a C infinity section of the bundle L-1. And now we have to compare these two things. And since we can plug in this equation, now we can work locally. So for example, assume that we have a fixed atlas for C, such that the bundle also trivializes on the U alpha. And that so we have a frame on each open set, and then these sections will become functions, and so let's write this down. Also, lambda will be a function because sigma alpha star will be the dual frame. And So what is this thing here? So d lambda over Si, product Si, will be exactly the same as d bar of lambda over Si. This is because Si is holomorphic. And if we write down, this is the product of these functions. Now basically, what happens here in all these kind of computations is that one has to arrange things in order to use the condition that Q is here. What does this mean in terms of the functions? This means that the multiplication of Q is 0, but the multiplication of Q is simply this section. And if we write locally, we get this. So this function, this local function, vanishes identically. This is the first thing one needs to use. And since this vanishes identically, we can also differentiate it. So if we differentiate and use the fact that these are symmetric, we can we would get this with a 2, and this also would vanish. Of course, we can forget about the 2. But, okay, so we were here. So this thing here was used to, we needed this to compute these functions here. So we have a decomposition like this for f time Si, and a similar one for f prime time Si. This means that the cohomology class, of course, is the same. So it will not change. This piece here is the original piece. This piece here is for the prime, for f prime, plus this object that locally we have written like this. So this means, this means what? That h prime is equal to h plus this. There could be a constant, but this is not completely irrelevant. Okay, now we have computed the second functions from the first, and then we have to compare these two expressions. So the first expression is the original one. And the second expression is the same, but with h prime. So the difference of the two, this is the second, will be simply this thing here. Okay. Okay, so now let's write down the differential of this derivative. I'm using prime to denote derivative with respect to d over dz alpha, the local coordinate. And so we need to show, to have that the two are the same, we need to show that this is 0. And plug in this here, we get and now use that SI is represented locally by this function. So this was a J, sorry. This is also a J because here is here also was a J. And then what we get so this is Fi, Fj prime alpha, and everything is multiplied by this, and sigma alpha. And here the same, not the same, almost the same. So in the end, we have been able to factor out these two pieces. This is exactly saying that Q is in the kernel of the multiplication, and this is the consequence. So we are using these two things. And this shows that this vanishes identically. So the first and second form are give the same result. And with the same kind of tricks, one can prove that, in fact, the result is a holomorphic section. So this is here. Okay, so this Hodge-Gaussian map is once you know how to define and how to prove it, is not so difficult, but is very strange to imagine it. And it will probably have other applications. But I don't know about them. So the application, the original application of Colombo, Pirola, and Tortora in the same paper was to show that the second fundamental form of, let's say, this inside Ag is a Hodge-Gaussian map. And before stating it more precisely, let's recall our setup of yesterday. So the local setup for studying the Torelli morphism is that so the Torelli morphism goes from Mg to Ag, and it is an embedding outside the hyperelliptic locus. This is, for me, is just a notation for the complement of the hyperelliptic locus, nothing more. So the local setup we had yesterday was that of Uranishi family. And here we got a local expression for the period map, which is the metric Z, the period matrix. So this is the local version of the problem. And okay, so in this case, to express the second fundamental form as a Gaussian map, as a Hodge-Gaussian map, one needs to use as a line bundle the canonical bundle. Then we have several important things that I now say. So let's look at we are identifying basically U with its image and are considering it as a submanifold of Siegel space. So let's see at this exact sequence on, in this case, how does it look like? And so here, if we put, if we choose the point that corresponds to some curve, so this is a point, this is the central fiber of the Kuranishi family. So this one is isomorphic to H1 of the tangent sheaf by Kodaira-Spencer, while this one is isomorphic to this space. And this one can also be seen as the dual of this. Sorry. So we can dualize this, this sequence. Here we would have this, and here there is pi. This is the differential of J. And if we dualize, we get this sequence. This works only if C is not hyperelliptic. So let's see a moment. Here there is the codifferential, and the codifferential turns out to be exactly the multiplication map here. Moreover, by Noether theorem, if C is not hyperelliptic, then this is onto. And so, the space here is exactly the kernel. So it is the I2 of this bundle. So this is why this has to do with the Hodge-Gaussian map. Okay, so can you read here or too small? Okay, yeah, sorry. So let's. I'm saying that this. If we dualize this one, we have here we go cotangent of Siegel, and the codifferential is the multiplication map. And this is onto, since C is not hyperelliptic. Okay, so let's write down. So this is J was the. So this map I'm computed. Okay. And so So let's state more precisely this result. So the precise form is this. Now this is denoted in this way the second fundamental form of JU here. So this is our version on the uniformizers of the second fundamental form of MG in a G. Okay, then this has to be computed where? If I take Xi and Xi prime, they should be in the tangent space to U, which is the H1 of the tangent sheaf. Sorry? No. It's a submanifold because U has a lower dimension. So yeah, this. No, you're right. So this is dimension 3G minus 3, and this has dimension going quadratically with G. So as soon as G is 4, this is bigger. Sorry? Yeah, this is kind of modular space. This is MG, and this is a G. Yeah, no, definitely. You're right. So, and we want to compute this. So we need to contract it against something. So this thing here belongs to the normal bundle. To get a number, we contract it against something which is in the dual of the normal bundle, and this is I2. So this will be a number, and the theorem is that this is a Hodge-Gaussian map like this. Where here this Hodge-Gaussian is a Hodge-Gaussian map for a canonical bundle. So let's repeat how it worked. If we use it for a canonical bundle, it will go from H1 of the dual of the canonical bundle, which is the tangent sheaf, to H0 of K times K. So this thing here so the Z is the right thing that we have to put because it is an element here, and this thing belongs to this one, which is the dual again of the same space. So if we contract with another element from H1, we get a number. Okay, so I'm really very slow. So so this is this says that that the second fundamental form can be computed using these maps. The next step, which is also done in the same paper, is to show that one can write a formula for the second fundamental form in terms of Hodge theory. So now let me describe this very quickly. So first of all, we have to define a form eta. So fix a point on the curve and consider this inclusion, call it psi. Then by Meyer-Vietoris, we have that psi induces an isomorphism on H1. So if we have a cohomology class here, we can immediately see it as a cohomology class on the whole curve. Next, observe that the sections of these bundles, so one forms with at most a double pole at X. These ones inject in the cohomology of the curve with a hole, because if I take an element here, alpha is holomorphic and closed on C minus X. So alpha defines a cohomology class. And this cohomology class is trivial if and only if alpha is equal to the differential of a function. But then what happens? The function is holomorphic, and if Z is a local coordinate around X, then alpha looks like this around X, in the sense that we allow a double pole. There cannot be a term in 1 over Z because of the residue theorem, since we have our curve and we have only one point, and we cannot have, so by the residue theorem, the sum of the residues of a form on the whole curve are 0. And so if there is only one pole, it means that the residue there is 0, which means that there is no term with this coefficient. The coefficient of this is 0. So next, so this is, the alpha is like this, and if alpha has to be the differential of f, it turns out that f has a simple pole. So if df is equal to something like this, then f is like this. But then f has a simple pole, but then this implies that f is an isomorphism between C and P1. And so since we are assuming of having a genus at least 2, this is not the case, which means that this map is injective. Okay, so let's go back here. Now here inside here we have put H naught of Kx of Kc 2x. Okay. This space Riemann-Roch has dimension equal to G plus 1. And now we can look at this space here, and of course it contains the forms with no poles. So let's say psi star of H naught to K K2x contains this here, but is of dimension, this is of dimension G, and this is of dimension G plus 1, which means that there is a line in the intersection between this and the other one. So this is a line, is the vector space of dimension 1. And elements here will look like something like what I wrote there. Locally, they will be like this. And so the only, we can use this coefficient to pick a particular form. And we decide that if we decide so let's call this way the one in which the coefficient is 1. And this means something holomorphic. Okay, so let me state just the end result. The end result is that Hg can be computed in terms of eta. Actually, in this sense, if the vector is a Schiffer variation. So if in this case, if it is a Schiffer variation, then Hg u zx has an expression like this. Where here the coordinates are chosen such that z of x is 0, fj is the local representation of a form fi, and okay, so this is the form, yes. This omega 1, omega g is a basis for H naught. And okay, and that's it. So this is a part which only depends on Q, the quadric, because our quadric is given like this. So this part is a kind of evaluation of the quadric in some point, and this is the object. And what is important for what I would like to stress is that this only depends, so it is defined in terms of Hodge theory, and in fact has some nice features of Hodge theory in the sense that it is completely hopeless. It's not hopeless, but it seems very hard to compute it explicitly. Okay, last thing I might recall what the Schiffer variation is. And Schiffer variation is a kind of special element of H1 of X. And they are constructed like this. X is a point then I consider this this sequence, and then I tensor it with the CX. So then we take the cohomology. So the first two pieces are 0. Then this one is one-dimensional, since it is concentrated on X. And so we have a map from C to this space, and the image is a line because it is injective. And the Schiffer variations are elements of this line. So the Schiffer variation is defined up to a non-zero multiple. So Xi of X is a generator of one can also make it more precise by using local coordinates. One can normalize this one to choose a particular generator, and this is needed inside this formula. So this formula is not very clear, and tomorrow I will hope I will tell you another formula that looks better at least. Okay.
So are there any questions?
Yeah. No, because it is the second fundamental form. So, sorry? Yeah. Yeah. Where exactly it breaks down? Harmonicity in a family. Probably no, for sure. Yeah, that's basically the only thing. You take the harmonic part, and you also take the.
Okay, then let's thank the speaker.